Hi everyone, welcome back. It's been a long time. I had a semester break, and yes, I know you're expecting the craft section because the channel is called Biochem and Crafts, and I promise it's coming. It is coming. I was sewing during semester break because I had finals and then I had a semester break. But I promise it'll come. I just have not had time to finish filming. Well, I did I did half of the video. Half the video is filmed, but the rest of it, I'm still working on it. So if it comes out in a long time, I'm sorry, but I promise it is still coming. So anyways, let's get into it. Restriction mapping. As you know, I always have a game plan, so let's get into it. First off, we have gene cloning. Next is endo versus exonucleases. Third, I'm gonna be talking about restrictive enzymes. I'm also gonna be talking about DNA ligase a little bit, but I know it's not in the game plan, but it's gonna be there. It's just gonna be like a short excerpt. And then we're gonna go into restriction mapping, or also known as restrictive mapping, or the basics. So let's get into it. Okay, so for gene cloning, the basics of it start like this. You have a plasmid, which is also known as a cloning vector for this kind of experiment, and then you have a eukaryotic chromosome, or like a section of a chromosome, whatever. But that chromosome contains a gene that you want to study, or a gene of interest, gene of choice, whatever you would call it. But it's the gene that you want to look at. And so an endonuclease will come in and cleave both the plasmid and the eukaryotic chromosome where you want to separate it so that you can get your gene of choice kind of isolated by itself. And it's the same endonuclease that will cut both. Once you have cut both the plasmid and the eukaryotic chromosome, DNA ligase will come in and glue them together. So it'll take the gene of choice and the plasmid, or the cut up plasmid, and put them together to get a recombinant vector. And we got the word vector because remember, I just talked about in plasmid, it's also called a cloning vector. So you get a recombinant vector because of the fact that you are combining both pieces of quote unquote DNA, or just both pieces. So then this recombinant DNA, or recombinant vector, is introduced into a host bacterium cell. And from there, the bacteria is able to clone, or kind of reproduce or replicate itself. And the idea is to get the recombinant vector into all of these plasmids, or you're just basically replicating all of this. You're replicating this gene of choice into all the bacteria. And sometimes in this case, so I have a couple of bacterium. I have one, two, three, four, five. One of them does not have a plasmid. So sometimes it'll replicate without a plasmid. Sometimes it'll have more than one plasmid. But for most of the time, you should be getting, if you do this experiment right, you should be getting at least, a plasmid per cell. Moving on into endo and exonucleases, there are two types, but for the most part, nucleases cleave phosphodiester bonds, okay? That is kind of the big deal there. So an endonuclease recognizes DNA sequences and cleaves at these specific sequences. So basically, endonucleases cleave at specific locations. Now, exonucleases cleave kind of at random spots and one by one. So, with endonucleases, they are kind of called the molecular scissors because they can cut DNA at specific parts and they cut away from the ends. Exonucleases can cut from either the 5' end or the 3' end, so it's kind of like a chop, chop, chop. Whereas endonucleases is kind of like, could be in the middle, could be, towards the side, but it's not going to be at the very end, unlike exonucleases that can start at the end and go, from 5' all the way to 3' end, or the 3' end. Okay, so moving into restrictive enzymes, are also known as REs. They are endonucleases, and as we just reviewed, they cut at specific locations. So, and restrictive enzymes, or REs, can be used to perform cloning. And I did talk about a little bit of an overview at the beginning, but types of REs include ECO R1, BAM H1, and KPN1, and the 1 is kind of the Roman numeral, and then the eco as in E. coli, and so on and so on. And so, kind of a little bit of a background is they were named because they prevented invasion by foreign DNA by cutting phage DNA when infected or upon infection. So basically, they cut DNA like scissors beats rock in like a rock, paper, scissors type of moment. or wait, no, scissors beats paper, not rock. What was I talking about there? Oh my gosh. Anyway, as I was saying before, I basically just made a fool of myself. So basically, REs cut DNA like scissors beats paper and rock, paper, scissors into DNA fragments. And this only works with dsDNA, okay? Okay, so REs can make two types of cuts that I have learned so far. One is a sticky end, or basically it's just a hanging end. So as you can see with the E. coli restrictive enzyme, um, it, the RE has cut um, from a palindromic sequence. And so as you can see for both the 5' ends for the E. coli RE, there is a cut right after the guanine on the 5' end, and then on the complementary side, there is a cut on the other 5' end. The next type of cut is a blunt end cut, so it's basically just straight down the middle of the DNA. And so cutting palindromic sequences are more effective for restrictive enzymes, but they are not limited to them. It just increases their chances of the cutting the sequence. Moving on into DNA ligase, basically we're just going to be putting it all together. And so to summarize what I said at the beginning and throughout all of this is that we have a gene of choice and we have a plasmid vector. And so this plasmid vector is cut by our restrictive enzymes on its MCS, or also known as its multiple cloning site, or also known as its polylinker, which is just located on that plasmid vector. Is basically just a site where it's just cut, and our gene of choice is kind of put into our vector with because they're complementary, so they have to be complementary. Otherwise, it's just not going to work. So both the vector and the chosen gene have complementary ends, either sticky or blunt, and they have to match up together perfectly to create a recombinant vector. And so, like I said, recombination is just combining. And yeah, that's pretty much it for that DNA ligase section. Okay, so restriction mapping is basically a physical representation of a linear sequence of fragments or DNA fragment, which look at the location of genes. And so how it works is basically restrictive enzymes, or REs, complete single digests, which means they cut once, and are run through gel electrophoresis to compare sizes and conclude the location of genes. Okay, so as you can see here, we have taken our cloned copies of our 5 kb DNA fragment and have run them through the gel electrophoresis by restrictive enzyme cleavage. And so after that, we're going to calculate our fragment sizes. You don't have to worry about that, but we're going to be interpreting them. So as you can see from our little table, we have our uncut DNA at 5.0 kb, our E. coli restrictive enzyme cuts at 4.5 and 0.5 kb. Then we have cuts from a BAM restrictive enzyme at 3.0 and 2.0 kb. And then we have both the enzymes acting on the cloned copies at 2.5, 2.0, and 0.5 kb. So once we have our table, we're going to analyze this DNA by putting them up against the uncut DNA and the ECO and BAM models, just to see any similarities. And once we do that, we are going to create some models. So model A has different estimations of where the E. coli and the BAM restrictive enzymes have cut, and so does model B. But the difference between model A and model B is that it doesn't work with what we had in our table for both enzymes cutting the clone DNA. So both the E. coli and the BAM cutting the DNA. So for this, we're going to have to go with model B, just because when you compare it to the table, there are cuts along 0.5, and you can actually kind of go back to the beginning where there was cuts with E. coli. There is a cut at 0.5, and so we know for sure there is a cut by the E. coli restrictive enzyme on 0.5. And so the BAM RE also has cuts as well, and you can also kind of just look at the table to confirm, but the cuts along the 5.0 kb fragment, or that DNA, is what you see on the table. So you kind of just have to infer and use, like, I guess, context clues to see if which models that you've created are most similar and what agree with the results from the gel electrophoresis. And that's pretty much restriction enzyme. Thank you so much for watching, and let me know what you think.